let's welcome our next speaker, who is Zenodia. Zenodia is a senior deep learning solutions architect at Nvidia. She's on a mission to help data scientists and researchers alike to accelerate their deep learning workload with ease taking advantage of her learnings and expertise. She will talk about better, faster utilizing your GPUs for deep learning workload. Very excited to hear about that. Welcome up onto the scene, Zenodia.
Thank you. Okay, well, today's topic is faster, better, utilizing your GPU for deep learning. Now, before I go talk about this topic, let me briefly introduce myself and the company I work for, and I promise you it has something to do with today's talk. Okay, so I'm a senior deep learning solution architect. That doesn't say really much things, but more interestingly, the company I work for, Nvidia, previously known as a gaming company. We produce GPU for gaming. Well, that's true. However, like every other company, we evolved ourselves into creating a full stack solution for deep learning. It is purposefully built. Now, I'm going to slowly walk through this because, this, again, has something to do with today's talk. If we look at the bottom hardware layer, if you have NVIDIA's GPU in any of those hardware systems, whether it is virtualized or in a supercomputing cluster, one of our DGX family, in one of the OEM computer, such as Dell or HP, or in the cloud, it doesn't really matter what it is. As long as you install the correct CUDA driver, that will expose you to have access to the CUDA-enabled libraries. What do you supposed to do with those libraries? Well, look at the blue layer, that's the application layer. This is where we provide state-of-the-art, GPU purposefully built Docker images for you to use. You can simply put around it. These environments are reproducible, portable, and scalable. Well, you can actually just stop here if you think that these Docker images, if integrating into your workload is enough, because you can DIY yourself. However, we also want to transfer our learning from industry bundled in a Python SDK, end-to-end for you, so you can take advantage of that. Some example, like Jarvis for conversational AI, Clara for healthcare and genomics, DeepStream for smart cities, and so on. All right, so we're really going to talk about this topic, better, faster, utilizing GPUs for deep learning. Today's agenda is like this. I'm going to present a challenge. Then I'm going to tell you this challenge motivates us to create a tool to help you to address to this challenge. It's called DLProf, Deep Learning Profiler. Now, this deep learning profiler, I will tell you how to get it. And we will walk through one iteration of this workflow with a very simple user case. Then we're going to conclude by comparing before versus after optimization using this tool. Let's get started. Now, the challenge here is that if you look at this graph, it's called TensorBoard. It is very often used by deep learning practitioner, data scientists, data engineers of the sorts. They use it to check the model in a visualized way, as well as tracking the training performances. Now, this graph is great and all. It just does not give you information about GPU utilization at all. It doesn't tell you whether there's a difference between using the data type floating point 32 versus floating point 16 in a layer-wise level. It doesn't tell you why some of your operations are not using tensor cores, which allow you to access to GPUs. Now, we wanted to address to this challenge, so we created this specific tool called Deep Learning Profiler. As you can see, this is directly plugged into the existing tensor board to give you a unified user experience. It gave you all kinds of matrices with regard to GPU. For example, if we're going from the left to the right, it gave you information of whether your GPU is idling, if your operation is actually eligible to use Tensor Core but not using it. Also, the last two pie charts tells you whether your Tensor Core kernel is efficient or not. Now, there's a lot of information. It still doesn't really help you. So let's turn our focus on the middle, bottom. It says recommendation. These sections is something we made specifically for you guys to take advantage of. So you can directly just clicking on one of those links and read those texts, and then it will give you a detailed explanation of what's being wrong and what you can do to correct it and optimize it. Now, remember I told you guys that, that particular slide has something to do with my talk today? This is about it. So we have already talked about whatever hardware with Nvidia GPU in it, the bottom layer. We already talked about, you have to use compatible CUDA libraries, is the driver. Now, to enable for you to get this tool called DOPROF, you need to pull and run the NGC Docker image. For TensorFlow, it has to be bigger or equal to 2003. And for PyTorch, it's called PyProf. It has to be bigger or equal to 2007. Then you can get to work. This tool is directly embedded. No need to install nothing. No pip install, no CMake, no build. It's directly inside of those Docker image. Now, let's look at the workflow. This is our simple workflow to help you to do optimization. You first run a profiling session like this, and then you visualize in the TensorBoard plugin DOPROF dashboard that we just seen. And then you take into the recommendation as well as analysis from this dashboard, and you take actions upon it. We are going to use a really simple user case to go through this one iteration due to time. So we're just going to run through one time. Before we do that, well, usually you cannot separate training the model with a data pipeline. So the data pipeline usually add a layer of complexity to things because you need to know what kind of decoder you're using if you're dealing with image. You need to know what kind of algorithm you're using in order to do augmentation and so on. Now, to simplify things for profiling, we're going to take away our data pipeline to piping real data and replace it with synthetic data. This allows us to focus only on the model training as in forward and backward propagation. That's all. OK, to evoke this profiling session is rather simple. The only thing you need to do is to select a few options. Those options like what kind of reports you want, the detail or the summary, or all of them. Where you're going to store it, how long is it supposed to be running, do you want to tag something, and so on. Once you decide on those options, you run DOPROF with these decorations, followed by your own Python script. That's simple. One command line, simple, and it's done. Then you can call out your tensor board, and then you will see the DOPROF dashboard as we're going to see in the next slide. So this is a naive run without any optimization at all. So obviously, it's going to suck. So if you take a look at the upstairs pie charts, they are all very bad. Well, you can use the operation is eligible of using Tensor Core, but it's not using it. The GPU is idle most of the time, and Tensor Core kernel efficiency is 0. Okay, so that is still not really saying much. Let's take a look at the recommendation section. This is exactly what we're going to wrap it around and take actions upon. The first two things is that enable XLA. enable AMP. We're going to talk in detail about this as our first action. We group these two into the first action. And the second one is that, well, tag the key node. Now, if you have your model with different layers, and you want to tag a specific node and say, I want you to take a look at it, focus from this point onwards, that's what tag a key node is about. We're going to do that too as our action 2. And the third thing is that, well, you need to pad your model shapes and sizes into the multiply of 8, because, our GPUs love the magic number 8. Now, before we move on from this naive run dashboard, I want you to remember 2 things. 1, the GPU tensor core utilization is 0, and GPU is idle around 80% of the time. Now, let's take our actions. Based on the recommendation from the dashboard that we have seen previously, the first actions we took is enable AMP. AMP stands for automatic mixed precision. As you can see, there's just 2 lines of code you need to add into your Python script. Then you enable AMP. So what does it mean? Look at the graph over there. You have your model layers. It will automatically take your model layers and cast the type from floating point 32 to floating point 16. This will allow you to actually access to the GPU tensor core and compute there. Those operations will directly have access to the tensor core on the GPU. So this will give you performance boost. Then we're going to enable XLA. Again, 2 lines of code. Then XLA is a native library from TensorFlow. It's a native linear algebra acceleration library. This library would take a look at the graph definition and we'll look at the operation and say, okay, I know this operation, I'm going to cluster them, then I'm going to compile them against the target hardware, which is the GPU in the selected hardware that you have in your home or in your office. Remember these first 2 layers. So these are the target hardware. Now, it would execute those operations, the cluster one, in that target hardware. So this will give you further performance boost. Now, after XLA, all of your operation, since it's cluster, will be renamed into XLA 01 and so on and so forth. So that's what we're going to do the next, because we're going to tag those after clustered operation. So here we go. We're going to tag one of the first node, 01, after XLA renamed, so that the iteration will go focus on this clustered operation onwards. The third action we took is a little bit drastic. So what do? We take the convolutional 2D functions over there, and we say we're going to increase the stride from 1 to 2. These kind of mimic the behavior of max pooling. So we're going to take away max pooling. And we're also going to replace the reshape, mat move add, and we're going to remove the ReLU, and now we're going to use reduce mean instead. So let's summarize what kind of actions we took based on the DO Prof dashboard recommendation. First things, the first action, enable AMP, automatic mixed precision, which allow you to access tensor core. 2, we enable XLA. Then we take the keynote. Then we reconstructed our deep learning neural networks in order to fit to the magic numbers of 8 and the padding and all that, so that it can utilize the tensor core further. Ready to look at the result? Well, remember that number 0 that we got from the naive run? Now that, we have 52% of utilization, just one single optimization iteration, taking advices from the recommendation from this DO Prof dashboard. The GPU were idle 82% of the time before. Now, it is down to 30-something%. Just one iteration. before we look at before and after comparison, let's summarize what we have done so far. We present you with a challenge. That is, you have tensor board, but don't have any GPU information. So we created a tool that's directly plug-inable into your tensor board called DOPROF. Then we run through one iteration of this DOPROF optimization, taking 3 actions from the recommendation from the naive run of the DOPROF. Then here we go. This is our before versus after. Did you remember we said that it's better and faster? The faster part is here. One iteration, 12 minutes, 25 seconds before optimization. After optimization, now it's down to 1 minute, 30 seconds. One iteration. So, use it, please. I want to take the opportunity to thank Gaia for having me here, and thank you all for listening in. I will now take questions.
Yes, thank you.
Yeah.
So let's start with my own question.
Oh, cool.
So for all the PyTorch users out there, do you have PyTorch support?
Yeah, it's called PyProf.
PyProf.
Yes, it's exactly the same workflow, but you just replace DOPROF to PyProf.
Okay.
Yeah.
Great. And so there is also an XLA version of PyTorch that
Yes.
is using the XLA backend. Is that supported?
Yes, but you need to use specifically the PyTorch NGC Docker image, so they were building XLA for you.
Okay.
Yeah.
So using the Nvidia official Docker image.
Yeah. Oh, by the way, this is for free, and you just need to register an account, and you just put and run it like any other Docker.
Okay. Cool. That's good. All the PyTorch users that probably were worried during the talk, they can now relax and say that it worked for them.
No worries. We have you covered.
Perfect. That's great. Yes. So there's a question from Daniel here. So what is the most common optimization recommendation suggested by the system?
Well, the most common one is that, the multiplier of 8, because, 8 is a magic number for us. That, you need to make sure that all of your layers, as well as your batch size, everything else has to be the multiply of 8.
Okay.
Yeah, it must be.
Okay.
Because it's a magic number.
Okay, it's the magic. Yeah, good. I thought it was like 3 or 11 or something.
Yeah, yeah.
Okay,
unfortunately,
well, 8 is the magic number. That's good. So actually, it's a common mistake that people do, that they do batch sizes and so on that are not divisible by 8.
No, yeah, that's true. And unfortunately, sometimes you can't really get around with this. Then you need to optimize in another way, like, to compensate it. Because your image is too big or something.
Exactly. So you have to do with 2 or 4 or something like that.
Yes,
yeah, okay.
yes. But then you probably need to write your custom plugin.
Okay.
Yeah.
Okay. So then there's a question from Jesper here. Is it possible to profile an application across domains, spanning from both CPU transfer and then also on GPU? Or are the recommendations architecture specifics?
Well, it's only about GPUs and our GPUs. So CPU is something we are considering to integrate into, the moving host to device, device to host, and so on, but not in this graphical interface. You have to use the command line tool, which, if you're interested, in the end of the thank you slide, there's links about it there. You can read more. Okay.
So then we have. It also, from the list of recommendations that you had, it's also seemed like you actually changed the architecture of the model that could produce slightly different results. Is that opinionated changes, or do you feel that this is? How do you decide what kind of architecture changes that you recommend?
Yes. Oh, well, basically, it is like experiences that we have in Nvidia. The max pooling usually is very expensive computationally. And the stride for convolutional 2D, usually if it's stride 1, stride 1 is an odd number, not to multiply it whatsoever by 8, But if you increase it to stride 2, you will see the difference.
Okay.
And in fact, we have actually a blog specifically talking about these tips and tricks and details of exactly what you should do when it comes to layer-wise optimization.
That sounds like a great idea. So you don't need to discover all these things while running the tool.
Yeah, exactly.
Okay. That was the questions that we had time for.
Yeah,
and thank you so much.
Yeah.
And here comes Anna with the flowers.
Thanks a lot. Yeah.
So now there will be a 10-minute break. So I hope that you all get up and and get some new oxygen into your systems. It's been a long day, and you all welcome back in 10 minutes when David Gillblad from RISE and AI Sweden and many other things is going to give the final keynote. In 10 minutes. See you all back then. Thank you.